Okay, welcome back to our Cyber Physical Systems course, and we are in Chapter 2. As I mentioned, hoping to finish Chapter 2 today, and I wanted to start with this slide, which is the one that I was trying to find as I ran out of time yesterday. And it shows the evolution of the PC 100 standard, and it also shows some good foresight, some good architecting for a system where you want to have some sustainability as things evolve. So you can see that on the far left side, you start with the ISA bus, and then when PCI came out, which is a major step from ISA, they didn't just get rid of ISA. They put that's a trade-off. They compromised real estate on the board to offer legacy because of the installed base of boards that were with the ISA bus. And as time went by, then it made sense to get rid of ISA. They gained some real estate on the board, but then PCI Express came about, which is kind of, that's where we are right now. PCI Express is still used a lot for high-end embedded applications, but they didn't get rid of PCI. They had PCI and PCI Express coexisting on the module. And then eventually, now these days, you only have a PCI Express connector, so you get back that real estate. So that allows us to put together nice stacks, and if you're still at this point, which should be a minority, if still any modules that are using PCI, well, it is simple enough to come up with a PCI to PCI Express bridge. So that would be, for example, if this is the PCI Express bus and this is PCI, you can have just a single board with both connectors, and that becomes a bridge. So a bridge is a component that allows you to translate from one protocol to another, or from the same protocol with different speeds and replicating connections on the other side. The key characteristic of a bridge is that bandwidth is shared. So you don't gain extra bandwidth, or you don't maintain all the bandwidth being the same through all the connections. So if you do that, it's not a bridge any longer, it's a switch in the lingo of network. So you can have a PCI to PCI Express bridge and then keep going with your stack and still support PCI legacy devices. So as an example of the form factor of the PC 104, which is, as I mentioned, is about 4 by 4 inches, this is a physical comparison versus other type of embedded computers. So PC 104 is not the only one. So you have EPIC, you have EBX, but you can see PC 104 really compact with the levels of integrations of components these days. On a 4 by 4 board, you can put, if you do a good design and good architecture, you can put a lot of functionality. So it gives you the ability to design very rugged, very reliable embedded system computers. So now, as we wind up the chapter over the next 20 slides or so, we want to shift gears and talk about modeling. Modeling, design, and verification in embedded computing systems. And why is it useful? Or more than that, why is it necessary for the systems with the level of complexity that we are talking about in this course. So we have to establish that if you have a simple system, then maybe modeling is not a good investment, because to do good modeling, it requires time. It's not free. It's not a quick way of doing it necessarily. Normally, it does require less time than doing a complex prototype, but that's not really, as we'll see, there are other advantages that you can never attain with a physical prototype. So we're going to talk about those. So let's pick on an example for in the automotive domain. So we know how complex automotive have become, and they will continue to evolve and become more complex as we, at some level, start embracing autonomous vehicles at some level. I don't think that it's going to replace completely people driving, but there's going to be a level of adoption that is not going to be minuscule or trivial in the near future. I say in the next 5 to 10 years. Okay? So if you have these designs that have critical components, such as a powertrain, a complex powertrain, you need to really model these complex systems so you can start exploring the trade-offs of how to meet complex requirements. For example, in a powertrain, you have to trade off exhaust emissions to meet the standards, to meet environmental standards, with fuel economy and regulations, and also for the market demands. Those sometimes, depending on the vehicle, fuel may not be a concern. I mean, there are many people, actually, one of the most popular vehicles in the U.S. is the pickup truck by Ford, the F-150, and it's not economic. And SUVs, large SUVs, are very common. So sometimes that's not the concern, but there are regulations nonetheless. So you have to trade things like that, market, regulatory concerns, and in complex systems, this is a theme. In complex systems, the trade-offs conflict with each other. And that requires good architecting. So good systems engineering and good architecting is to negotiate those conflicting requirements. From a client perspective, from an extreme position, the client would say, I want everything free now. So that's the extreme. So good architecture is to move that to a sentence that looks like this: you will get this at this price by then. And then the client is still going to be happy with that. Okay? So that is good architecture. So that requires careful exploration of trade-offs. And if you think about a complex system, an expensive physical prototype, and you have to explore trade-offs and different ways of doing things, that becomes really unmanageable, becomes very expensive, takes a long time. So models serve that purpose, because now you have something that you can manipulate in a computer and look at these trade-offs. And the underlying assumption is that you have a good model. We're not talking about a simplification. A good model is not a simplification. You still have a faithful model that expresses the complexities of the system. So modeling is very important. For example, so this is a model, and if you recognize the icons, this is on in LabVIEW. So one of the tools that we can use. And I'm much more partial to MATLAB. And actually, as of yesterday, we are going to get System Composer added to our MATLAB suite. So I requested that, and the request was granted. And that is the newest tool by MATLAB for system design, because that is the trend. That is the trend. And I think future students of systems engineering, they're going to be happy that they're not going to have to use core anymore. So we'll be able to use MATLAB System Composer, which is kind of an overarching theme here. You know, we try to basically use MATLAB as much as we can in the courses. So that is going to work out really well. I'm really happy about that. We already have a state flow, which is part of the system suite, and we also may get sim event from into MATLAB Simulink. So that's going to be, we're going to have everything for system level modeling. But this is a LabVIEW model, and we have some sensor fusion going on. So we may have some sensors here, and we have some user command or control logic here as an input as well. So we can do some sensor fusion algorithm here, and that becomes some output that drives a plant. So as a description, let's say that previous figure is a system that tracks engine torque in an automobile. And what we want is a steady state, accurate steady state of that torque to some set point that may be an output of the cruise control subsystem. At the same time, we want to minimize brake and fuel consumption, because every time you brake, whether it's the user or the cruise control system, then you have to accelerate. So that increases fuel consumption. So you want to minimize that event. And also you want to minimize the coefficient of variation of the pressure that you are exerting on the powertrain. So you have parameters. You come up with a model that is faithful. Now, for this model to be faithful, if you go back to our first chapter, you're going to need a domain expert. Maybe a system, and you're trying to do the control system, and a sophisticated embedded controller for this system, but you need someone that mechanically understands the physics and the trade-offs of the whole powertrain. That's the domain expert. But through that interaction, you're going to come up with a couple of tuning parameters. And let's just call it Q and R. So once through the interaction with a domain expert, you have a faithful model, now you have a tool where you can start exploring what is the best trade-off and the best value for such parameters, so you optimize for, in this case, fuel consumption, minimization of fuel consumption, which is a optimization, and the coefficient of variation. So you can do that and come up with your algorithm and your overall system. Tools like LabVIEW and MATLAB, then you can extract code if you're going to target, because at this point the model is implementation independent. We haven't decided how we're going to implement it, and it could be that we have to, let's say, if it's something that requires a lot of performance, maybe there is no embedded processor that can do it, and we have to do an FPGA. So tools like LabVIEW, MATLAB, and so forth, it will give us RTL, so we can, at least as a starting point. In reality, none of these things are 100% plug and play, such that you can get rid of the human, but it will give you a very good starting point where you can start synthesizing in an FPGA, or if you're going to use a processor, it will give you an excellent starting point of C code that you can start compiling into a processor. So that's what we mean by easy transferring that to hardware. I mean, easy is that maybe you just have to massage it and account for 10% of the work that you would have to do if you were doing it from scratch. And that's great. That's a great increase in productivity. So if you look at modeling from the system level perspective, and as it pertains to the hardware part, to a hardware that is going to be coexisting with software, any shortfalls of the classic software development process that could go back and pollute the overall system engineering process, modeling can help attenuate that greatly, because hardware design with a software development approach is a disaster. It's a disaster because the software approach, because it's software, changes in reality are very inexpensive and can be done much more rapidly than with hardware. So that works well for software, but it doesn't work well for hardware. So the infusion of modeling techniques, including not only the hardware, but the software at the system level, attenuates that consequence. So overall, it should be clear that it mitigates risk in being able to look at what we're going to do early on and look at trade-offs. Then it also helps us with communication. So teams, if teams are large, they are distributed. A model is accessible by anybody in the world. While if you have a physical prototype, then that has a geographical limitation. Not everybody can take a look at that. So it has it also tends to be graphic in nature. So if you think of a global development infrastructure, it would be better for those colleagues in maybe some other countries that don't speak the language, where some of the documentation is being put together, to be able to look at something graphical that actually has the girth of and the discipline of faithfully expressing the system that we're trying to build. So there are a lot of benefits to good modeling techniques. So going back to the constraints, why is this important? Again, what are the characteristics and constraints of embedded systems for complex cyber-physical systems that makes modeling effective and necessary. The real-time aspects. The real-time aspects. So we are dealing with a physical part that has its own bandwidth, its own reaction time. So we have to meet that. Some of it is slow, some of it is faster. It's all relative. If you have something that is the physical world is slow, but your algorithm takes a very long time, for all intents and purposes, that's a fast changing physical plant, because what you need to do takes a long time for you to react to it. So relative performance and response time can be optimized because those are characteristics of these complex systems. Embedded systems also have very stringent size physical requirements, size, weight. They also have very stringent power requirements. A lot of them are operating on batteries, and because of the small physical spaces, they have very challenging, which is part of power dissipation, cooling requirements. So the implications of dissipating a lot of power is also that now you have to come up with a cooling mechanism if free air is not enough by convection. They also have safety and reliability requirements because they are being put in applications that have those type of implications. And they also have very tight cost constraints. Not all of it, but a lot of embedded systems have, if they are going to target, for example, the consumer market, they're going to have very tight cost constraints. So before you just go and make something, you want to make sure that you have optimization in your process. And optimization with complexity, which contains some level of very thoughtful and engineering-driven, educated exploration. And I say all that to make a distinction. It's not trial and error. It's not trial and error. But it's not something where you can solve an equation. But it's not trial and error. So you have to aid yourself with models to be able to explore the huge space of possibilities and try to narrow down and optimize your system according to the constraints. So the correctness, let's dive into the timing issue. The correctness of the response and the behavior of the embedded system or the real-time operation. For example, these are some of examples. It may depend on periodic inputs. So then, if you know that and you can anticipate, then you can model and come up with the most efficient schedule. So you can schedule things. But what if you have something that is not periodic, something asynchronous events? Then one way to approach it is to estimate through your modeling what is the worst case and design for that. That's one way. But then you can also look at the ramifications of having an isochronous behavior. That's different than synchronous. So synchronous, periodic, and you're always responding, and you're guaranteed to respond because you can respond by that period of time on the schedule. So you can meet the schedule. Then you have a periodic, which if you are going to meet all cases, you have to design for the worst case to meet 100%. And that may be what you have to do. But maybe that's not necessary. And you can explore the ramification of somewhere in the middle called isochronous, which means that you try to respond sort of a period that conforms to the cost, to the complexity, and other constraints, but there may be some requests that basically go by the wayside. You cannot respond to everything. So how do you measure the implications of that? How do you measure the implications of that? Well, a good way is through modeling. And just to put it in perspective, a good example of isochronous delivery is media streaming. Okay? So if you have a pop or a click on your Spotify stream, nobody's going to, complain. And that's a packet that got dropped. And if you sometimes get a frame missing in your Netflix stream, you're not going to cancel your subscription. That's isochronous. Sometimes things get dropped. It's not the end of the world. But those frames are coming on a schedule. And most of the times, we can react to them. But if we are transmitting a database of payroll data, then we better not get anything dropped from there. So there are, it's good to understand the application. So modeling helps us do a good job and minimize, in this case, pessimism in the design, which is not good design. So other things that it allows us to do, look at physical issues like power. You can have power budgets that are modeled based on activity of the different components. So you start getting an idea. You start getting an idea of what type of power before you have something. Of course, that is, you have something, and you measure the current, and you measure the voltage, and you measure the power, then you know exactly what the consumption is. But now you have to have it built. But how do you know before that case start being rendered in the mechanical CAD package that it can handle the power dissipation and perhaps any cooling requirements that may be necessary? So it allows you to do things like that and take into account things like non-rectangular and non-planar geometries. So one of the things that is becoming, it has been used for a while by the military because they can afford some of the more expensive manufacturing approaches, is flex PCBs. So these are PCBs that are not on the rigid material that you may be used to, but they are on a flexible substrate. So because of that, you get a lot of, flexibility on how you package electronic components. So it allows you to model things of that nature. So look at the different ways of integrating and packaging electronics with other components, electromechanicals, and so forth. So remember, we talked about the logical architecture or structure and also the physical So what we're saying here is that you can take a look at both through modeling and the impact. What are the impacts of physical packaging? One is heating implications, power dissipation, or power dissipation cost, heating, and things of that nature. Through all that, you're really looking at risk. Yeah, the model is not the real thing, but the better your model is, and the more you explore the alternatives, you are really mitigating risk by at least making sure that the obvious wrong choices, obvious when you analyze them, they may not have been obvious without some analysis, but obvious with analysis, those that you know, yeah, that's not going to work. Now that we put it into the model, we can see that that's not going to work. Those go by the wayside quickly. And you start paring down your choices very, very nicely and very quickly. So at least it gives you that. At most, you can come up with very close to your final implementation through modeling, such that perhaps you have one prototype, another pass, and that's it, instead of 5 or 6 prototypes. So that's some of the modeling benefits. It also helps you with reliability related exploration. You can model reliability. Reliability is something that is very close to physical phenomena, and that's something that can really be modeled very nicely with equations, depending on the material, depending on the field. And then you can start, depending on the reliability constraints or requirements that you have, you can model redundancy approaches. But that's a way to increase reliability through redundancy. So you can start looking at fault tolerant techniques, for example. Tied to reliability is safety. Some of these embedded systems are mission critical, depending on the application and where they are deployed. Now, when it comes to safety and also to reliability, we are talking about the system. So we have to talk about not only the reliability of the physical hardware, but also the reliability of the software. That's equally important. Software reliability is a field that is less understood, much less understood than physical hardware reliability. And modeling, by being able to simulate very quickly the behavior of the system, including the software, may help or will help flesh out and highlight issues like deadlock and things of that nature that may happen in software operation and cause unsafe situations. In that context, since we're talking about the system, modeling helps us with the trade-off of hardware and software partitioning. That's another space in which to optimize our design. So the idea is, how do we come up with a good model that affects what we're trying to do? We're trying to design a system and ultimately realize it. How can we do that So we need to have a model from which we can actually derive hardware. So that's important. And let me say one thing. So I heard that someone described that a good engineer needs to pay attention to detail. And I said, no. There's a word missing there. And it changes everything. The word is necessary. A good engineer needs to pay attention to necessary detail. Okay? Because if you're just worrying about everything at the same time for complex systems, you'll never get anything done. Or you get distracted, being pulled in so many directions that you cannot focus and execute. So that's not a good thing. So the magic and the craft is to be able to first know which are the necessary details, and then just focus and pay attention to those. The identification of the details and the follow-through to pay attention to those. So we want models in the hardware side where we can derive enough hardware to implement and hopefully synthesize. On the software side, we want a model that has enough meat to it that we can perhaps derive code that we can compile. And then we need to know in our modeling process how to combine bottoms up and top down modeling strategies. We want to reuse as much as possible. We don't want to every time create models from scratch, from the lowest level of the hierarchy all the way to the top. No, we want to be able to reuse. So a reuse strategy and a modularity strategy, those strategies are important as we refine our models. So the key here is to have the right level of abstraction. Have the right level of abstraction and the trade-off of the cost of the model, how long does it take, the accuracy of the model, and ultimately, and most important, the outcome of the model. What are we going to get out of it? Yes, we get information, but can we get more? Can we get something that we can actually start and help us with the implementation, both on the hardware and the software side? These things are conflicting. So the modeling strategy becomes also an optimization problem. And that's why these things are complex. It requires a lot of thought and good knowledge, a lot of knowledge about what's available and when to use it. So some examples that are available for system level modeling are language and synthesis based type approaches, mainly on the hardware side. We also want these approaches to call for implementations that, as much as we can delay it for, be platform independent. So we want that freedom of delaying as much as possible the final implementation where we choose a platform. And you can think of a platform as a specific vendor or a family of products from a specific vendor. Those are platforms. So the generality, at that level of abstraction, the generality of your model becomes important, and that's why standard modeling descriptions are important. because they are not going to be tied to the platform. Okay? Makes sense. That makes sense. So, is that trade-off? Level of abstraction with the intentionality of being able to implement, the intentionality of implementation, which the being agnostic to specific platforms. So you can see how these are not decisions that you can just calculate how you do it. So it requires this awareness, which is one of the main things that I'm trying to share in this course. That awareness of how to go about designing these complex systems. So the goal of model-based design is to describe these components that doesn't commit to a specific implementation. At some point you have to commit, but for as much as possible, you can optimize your system as much as possible at a certain level of abstraction, then you can refine your model and approach that commitment, but then you already are carrying something that has a good level of optimization. So it's neither top-down or bottom-up, but it requires both. So think of library creations, model reuse, modularity. There is a lot to be said for reuse if it's done right. If you're always thinking in terms of your model creation and your model repository building, that this is something that you want to use in the future. You may want to put an extra port on something, or maybe add a little bit of functionality, or make something a little bit more general, and have that trade-off always in your mind, because it may not take a lot more just to make it so that something is much more useful than just the specific application that you're making it for. So that's important to take into consideration. So ultimately, after you have these models, and you refine them, you want something that you can actually implement, whether it's hardware or software. And also be aware that there are limitations. There are limitations, as I mentioned, with code generated, whether it's on the hardware side or the software side. There are limitations on the code that is generated, but it's a good place to start. You can refine that. Now, a lot of the modeling, it's not all of it, but a lot of the modeling you'll see that is based and focused on functionality. So functionality is one aspect, the other one is performance. So those are not well understood, although the research and the field of model-based design for system-level design is progressing at a very nice pace, but that's not as much understood as modeling functionality. So there is some trial and error that normally engineers have used to get the timing right. This is when I say this, I'm talking about complex high-performance systems. Of course, if you have a low-performance system, you have all the time in the world. But if you're pushing the performance of what can be done with a specific component or platform, then looking at the behavior and the timing-based reaction of these components, people rely on trial and error. So the challenge is for these complex systems that we're talking about, is how do we get the field of system-level model-based design and the research that is going on there to address in a more scientific, engineering-based, and systematic way the issue of timing, which again may be synchronous, stochastic, or somewhere in the middle. Because there is still a lot of worst case design being done, a lot of worst case design, but as we will discuss in the next chapter, the way that we envision these systems to proliferate and really change the way that we live, worst case design is just going to be a barrier, because it's just going to make the development too hard, too long, and too expensive. And the cost, not the development only, but the actual cost of build of these products. Now let's talk about validation. So validation is the process of knowing that your design is correct. Now you did your design, and you went through the process of optimizing, but now, and that includes some testing, in the sense that to know that you have optimized something, you were looking at constraints, and you knew you were getting the right answer, but you have a very specific boundary around that model for that exercise. So validation is also a challenge. How do we do that at the model level? How are we going to do it? And that is going to require also modeling that external world, modeling well that physical plant, and being able to bring in that expert domain knowledge into that modeling process. Because we're going to be very good at coming up with these complex systems, but we're still not going to know what that physical plant is. It may be a chemical process. It may be a biological process or entity. It may be an ecological system. And these are things that are other domains. So bringing that in and getting good models for that has great promise to do that validation in the modeling realm, in the modeling world, in the virtual world, but that's even at a more earlier stage, and that it needs to advance to, and it's going to advance for us to be able to take that into account in these complex systems. Because that's where you really start looking at more of the safety and reliability issues. So right now, as I mentioned safety and reliability modeling, but that's a bit limited. You can still do some of that in your initial modeling, but you get definitely the functionality. That's number one. You can get functionality through modeling very well. Second, timing. Then the validation is the one that is even further behind, as we look at the interaction with the actual environment that the system is going to deliver its mission, and you look at issues of safety and reliability that are very important. So how do we envision for this complex cyber-physical systems, the validation process. It is going to be iterative, that's for sure. So we envision several steps. Step one, we get the functionality requirements. So we can have an architectural model. So an architectural model, as I mentioned, picking the best components and interfaces to meet the functionality according to the constraints, such as cost, power, and so on. And you can develop a model for that. Then, through the mapping of interfaces, you can connect your model through other models. And you do some more simulation. Now, some of the approaches that are being looked at is cost-based algorithms, and that evolve into finite automata approaches to simulate the whole system together and be able to optimize it. So cost functions, the establishment and the predication of cost functions are a very nice way to do system optimization. So you can assign costs to different choices, and that helps you weight. That helps you weight and guide what is the overall global optimum solution. So hardware abstraction lends itself to that approach because you can assign different costs to the actual dollar cost. So that can have a cost. And things like CPU load, bandwidth of the communication network. So that allows you to, via these cost functions, check your model for a level of optimization in a manner that, since it's mathematics driven, that you can say that whether you are minimizing or maximizing the cost function according to the constraints, and then you can actually say that's an exhaustive solution. That's a global extreme of that cost function. So that's great. And if it's not, then the tool can tell you. And because the way the equation is built, then you can trace back to what are the elements that feed the part of the equation that may be causing the violation, and then you can work on that part of your choices. So, for example, CPU load is too large because I want to be able to only utilize the CPU 5% of the time, so it's sleeping, so I can save power. But the CPU is doing it, but it's busy 90% of the time. But if I go get the other CPU that can do it in 10%, but that costs more. So you got all this, and through cost functions you can start looking at those trade-offs. And also infuse counterexamples in the modeling and simulation process. You can say, what if we do this and force some constraints to be violated to see what happens to the overall behavior and the meeting of the requirements of the system, the meeting of all the constraints. So this technology has a lot of promise. Not here yet, but that's one of the things that is going to be required to deal with the level of complexity that we're going to be talking about in the next chapter. So that's the end of the chapter, and what we've done here is concisely gone through the big picture aspects of embedded systems in the context of complex cyber-physical systems, gave some examples of that, and what I hope is that these ideas, these important, very important, big picture ideas, to be successful in anything, you have to understand the macro and the micro. So your 411 course, that's the micro. That's where you're doing the actual code to do things. But keep in mind that you're going to these exercises to get the fundamentals. But that's not what the job is going to be. The job is going to be dealing with these things. So you have to, hopefully between these two, you have to make that transition to utilize what you learned there to think in this manner. Okay? So just to summarize, we went through an introduction at the beginning of the chapter. We talked about the importance of standards, mainly in the context of communication and interfaces, interface protocols. Then we talked about hardware architectures through an example of the PC 104 and the evolution of that architecture and how sustainability was taken into account by how the standard has been evolved, specifically with the connectivity of from ISA to PCI Express. And then in the last 20 or so slides, we all together talked about modeling. That included design metrics and constraints, and part of that, of course, is that model was of the whole system, of the hardware and the software, so intrinsically we were also talking about hardware, software co-design, and also partitioning, because if you're designing both part of the system, a natural consequence of that is that, and if you're optimizing the system, a natural consequence is that you are partitioning and optimizing the partitioning between the hardware and the software. So that's the summary of the chapter. And with that, we'll conclude and finish for today. Thanks. Thank you very much.